Now I want to talk about constraints and Berea method. So we have a function here, fx is equal to x squared plus 4x plus 5. And we can have two types of constraints. One is equality constraint. The other one is inequality constraint. So for this function, equality constraint will be something like this. X is 5. X can be only one value. Our optimal X should be also 5 to satisfy this constraint. Inequality constraint is something like this. X is greater than 1. We know that our X opt is -2 and our function becomes 1, which is the minimum value. So when x is greater than 1, our constraint limits our search in this blue region only. So when x is 1, we have this minimum value, which is 10. Doesn't look like 10, but it should be. And I will introduce a method called the Berea method to deal with this inequality constraint later. Regarding equality constraint, we can think of a different function f of two variables, x and y, and this equation can be plotted in a 3D graph. So here we have function fx and x here and y here. And this function fx will be something like this. And let's say we have constraint, which is y is 5. Again, this is equality constraint. That means y must be 5. And we will have a cross-section of this fx function. That cross-section will be similar to this 2D plot that we have on the left side. The goal will be finding this x opt value. Another way of looking into this is this. This function fxy becomes fx5, and this is x squared plus y squared, which is 25, plus 3x plus y, which is 5 minus 2. So this becomes x squared plus 3x plus 28. So you can consider this as a function of x, and this will be a parabola. Using the gradient descent or Newton's method, you can find out this x opt given this constraint, which is y is 5. The Berea method is a way of transforming an inequality constraint problem into an unconstrained problem. Once you have an unconstrained problem, you can use the gradient descent or the Newton's method for optimization. Now we have this function fx is equal to x squared plus 4x plus 5. We have inequality constraint, which is x is greater than 1. And we want to convert this into unconstrained problem so that we can use the gradient descent or the Newton's method. Let's have blue color for this function, which has this part identical as this f function in black, but we have another term here, negative b log base e. So this is a natural log x minus 1, and this b is positive real number, and this x minus 1 comes from inequality constraint. This can be re-expressed as x minus 1 is greater than 0. So this x minus 1 is shown here. By making this b very small, we can make our function f of x almost identical to this original function f of x in black. Because if b is very small, then the whole value here will be close to 0. Now I want to explain why we have this term here. Let me review the basics of a log function. This x minus 1, let's call it a. So we have a is greater than 0 now. And what is this log base e a function? So let me plot this function, and note that a must be greater than 0 because we will have a function something like this. So we know that a must be greater than 0. And what if a is 1? If a is 1, then log base e 1 becomes 0. So this must be 1. And what if a approaches 0? This log base e of a approaches negative infinity. This also means that x approaches 1, right? because a is equal to x minus 1. If a approaches 0 from the right side, x is approaching 1 from the right side as well. And another thing that I want to show you is this: negative log base e of a. This function will be an upside down function. But as a approaches 0, this time negative log base e a approaches a positive infinity. So again, this means that as x approaches 1 from the right side, negative log base e a approaches positive infinity. Now, this is a, and this term here with the negative sign is same as this one here. This function, f function in blue, is basically a function that has a positive infinity value as x approaches 1 from the right side. When b is very small, it will be almost same as this fx in black. But as x approaches 1, again, negative log base e x minus 1 value will approach positive infinity. So it will be something like this. Now our function has a new shape. And if you use gradient descent method or Newton's method, and if you start here, eventually you will reach this minimal value instead of reaching this point. And that's what we want, right? Because x must be greater than 1. And this is called Berea method because by transforming our original function, we have a new function with this barrier.